Have you ever wondered why vector spaces are so crucial in mathematics and physics? Well, buckle up, because today we're diving into the world of vector spaces, an intriguing concept that has far-reaching implications in various fields of study. A vector space, also known as a linear space, is not just a mere collection of vectors. It's a playground for vectors, where they can frolic around, add themselves together, or even multiply themselves by numbers, which we call scalars. Scalars can be real numbers, complex numbers, or generally elements of any field. Now, you might wonder, what gives a set of vectors the privilege of being called a vector space? Well, there are a few ground rules that a set of vectors needs to follow, known as the vector axioms. Firstly, vector addition should be commutative. This means that for any two vectors, the order in which you add them shouldn't matter. So if you have two vectors, u and v, adding u to v is the same as adding v to u. Secondly, vector addition should be associative. This means that if you have three vectors, u, v, and w, you can add u and v together first, and then add w, or you can add v and w together first, and then add u. The result will be the same. Thirdly, there must be a vector that plays the role of a zero in the vector addition. This means that when you add any vector to this zero vector, you get the original vector back. Fourthly, each vector should have an additive inverse. This is a vector that, when added to the original vector, results in the zero vector. The fifth and sixth axioms deal with scalar multiplication. Scalar multiplication should be associative, and it should be distributive over vector addition. Vector spaces are not just a mathematical curiosity. They are a fundamental concept that finds application in many areas of mathematics, including linear algebra, geometry, and functional analysis. In physics, vector spaces play a crucial role in quantum mechanics and classical mechanics. There are various examples of vector spaces. The set of all real numbers is a vector space over the field of real numbers. The set of all complex numbers, all polynomials with real coefficients, all matrices with real entries, and all functions from the real numbers to the real numbers are all examples of vector spaces over the field of real numbers. In summary, vector spaces provide a powerful tool for representing and manipulating mathematical objects. They offer a framework for understanding and solving problems in many different areas of mathematics and physics. So, the next time you come across a problem involving vectors, remember, it's all a part of the big, beautiful world of vector spaces.